Okay, so we now turn to the first objective of inference that we want to discuss in this lecture, and that is estimation or parameter estimation. And we're following on from what we've said already. So we've got observed data, which are assumed to be realizations of a random sample from a population with a joint density f x given theta, theta being the parameter. Now, parameter estimation or point estimation, we're going to use the observed random sample, the observed data, to infer aspects of the population distribution. Specifically, we're going to treat theta as an unobserved population parameter, and our objective in estimation is to use a sample from the population, to use the data to estimate a value for theta, some element of theta, or some function of theta, say tau theta. And there are different methods or estimators we can use to calculate parameter estimate, and we'll look at just two of the most common ones today, but we'll also talk about how we determine the best method to use. What's the best estimator we should use to estimate some parameter? And in order to establish that, we'll look at how we can evaluate different estimators. So we're going to start with some definitions, and as I say, we're building on what we've just discussed. Now, an estimator is very similar to a statistic. In fact, an estimator is a statistic. But let's just come up with a formal definition before we deal with that. An estimator is a way of obtaining an estimate of some population characteristic or parameter. Like a statistic, it's just a rule or function that we apply to a random sample. So it's formed as a function of random variables x1 to xn. Again, notice the uppercase to denote the fact that we're dealing with random quantities. So an estimator is a statistic used to estimate a parameter theta, but it's a statistic that's targeted. It's targeted at estimating a parameter. It's not just trying to describe a random sample. It's trying to estimate a parameter. So in that sense, estimators are statistics, but not all statistics are necessarily estimators, because not all statistics are aimed at estimating a parameter. So for example, earlier on, we were looking at representing the distribution of a random variable via order statistics. We weren't actually talking about estimating parameters, we were just trying to describe the distribution. An estimator is different. It's specifically targeted at trying to uncover or infer the value of a parameter. So that's the first thing, estimator is statistic. It's also, of course, a random variable, which is why we're using uppercase letters, because it's a function of the values of a random variable. Same as a statistic. If it's a function of the values of a random variable, it is in and of itself a random variable. That's an estimator. An estimate is a realized value of an estimator when a sample is actually taken. So we estimate theta using W and observed data. The estimate is any function of the observed data, and we denote it by theta hat. That's our estimate of theta. We use the symbol hat to denote it's an estimate, and it's a function of the observed data. So estimate differs from an estimate. That's smaller case because it's an actual number we get when we apply it to real data. This is uppercase because we're still dealing in the realm of random variables. Now, because an estimator is a random variable, it has a sampling distribution. And the sampling distribution, or the distribution of the estimator, we refer to as the sampling distribution. And it's the distribution of the estimator for all possible random samples of size n that we could take from the population. And we're going to denote that distribution by Fw for estimator W given parameter theta. That's the sampling distribution. So just to make these kind of concrete, the sample mean, which we've come across before, we called it an average in a statistic, but now we're going to call it an estimator because we're going to use the sample mean, a function of a random sample. It's 1 over n times the sum to n of random variables xi, sum of I equals 1 to n of xi. And we're going to use it to estimate the population mean, or the expected value of a distribution. Now, an estimate is computed by applying that sample mean. So we write that in lowercase letters. we apply the sample mean to actual observed data xi. So in R, we randomly sample 5 values from a normal distribution, which we specify with a mean of 10 and a variance of 4. We just use this code here. So give me 5 values from a normal distribution with mean 10, variance 4. That produces those numbers. Applying the sample mean, so we just calculate the average, yeah, this expression here, we apply it to those data, and that gives us an estimate of 8.54685. We repeat this process a second time. Sample again from the normal distribution, take the mean value by applying the sample mean. That gives us a different estimate. This time it's 10.1. So we've got two different estimates calculated by applying an estimator, the same estimator, to observed data sampled from the same distribution. So that's the distinction between an estimate, these two estimates here, and the estimator, which is the method or the function that we apply. And when we do apply it to real data, we get these estimates. Okay, and we can repeat this exercise many times, as we've done here. And when we repeat this exercise, we're essentially able to represent the sampling distribution of our estimator. So to get this graph, what we've done is 1000 times in R, we have sampled 5 values from a normal distribution with mean 10, variance 4. We've collected these values and then we've plotted them. And this shows how the estimates vary. And this is essentially a representation of the sampling distribution of the estimator. Its mean is about 10, but you can see it is roughly symmetric about this point, ranging in this particular graph from around 7 to around 13.